All right, now let's talk about crystal structures, which really has to do with the very unique 3D shapes that molecules can have when they're solids. Okay? We spent a little bit of time talking about gases and all the equations that you can use to describe behaviors of gases. And we spent a little bit of time talking about liquids and movement and how fluid they are and things like that. But we didn't really talk about solids too much. Okay? Solids are the most difficult phase to model because the particles, whether they're ions or atoms or molecules, are super, super close to each other. And so because of that, they have extremely strong intermolecular forces. And one of the things about the kinetic molecular theory was I was disregarding or ignoring these intermolecular forces because I wanted them to be weak so that the equations kind of worked out and made sense. And here I can't do that because they're very, very strong. So as far as solids go, we're going to kind of focus on two different kinds of solids. Okay, there are amorphous solids, which basically means that they're disorganized clusters with no long-range order. Think of them as kind of blobby and they're moving around. Or they can be crystalline solids. And in the crystalline solid, there's a highly ordered lattice-like assembly. Okay, so we're going to focus on the crystalline solids, where things are very repetitive and orderly. Okay, amorphous would be more like a kind of Play-Doh kind of clay that doesn't really look the same everywhere. It doesn't really have like a long-range order. Okay, and so focusing on the crystalline ones, it turns out they have different shapes, different ways that these crystals can come together. Okay, and the way that these crystals come together is something called a crystal lattice. So let me show you what these crystal lattices look like. Geometrically speaking, there's actually 14 different ways that you can create different lattices, which are called the Bravais lattices. But at any rate, out of all of these 14, the only ones that we really care about are the first ones, which are cubic lattices. Okay, and so if you think of a cube, it has all the sides exactly the same. Okay, same lengths. And also all the angles are 90 degrees. Okay, so everything is perpendicular to everybody else. Okay, and so even though there are other arrangements that are possible for these lattices, we're not going to worry about them. We're just going to focus on the cubic arrangements. And within the cubic arrangement, you'll see that there are three. Okay, and so let me zoom in to the cubic lattice and show you what these three different possible arrangements are. So the first one is called a simple cubic cell. And so what happens in a simple cubic cell is at each vertex or point, I have an atom or a molecule or a particle in general, and they align themselves around a cube. Okay, so I would have 8 little balls, right? We're assuming these are perfect spheres, each at each point along this cube. This is called a simple cube. The problem with the simple cube is there's a lot of wasted or empty space in between these balls. And I want to try to maximize how efficiently I can pack these little balls inside my little cube. Okay, and so there are actually 2 other ways to arrange these objects in a cube and have it be a little bit more efficient in terms of how many balls I can put in there or how many particles I can put in there. Okay, so the next one is called a body-centric cubic, or BCC for short. So what happens in the body-centric cubic is I have an extra ball seemingly hovering in midair, but it's not really hovering in midair because it's actually touching or tangent to the other spheres that are on the outside, right? So there's one here, there's one here, and there's one right there. And these are all tangent or touching each other. So now I have one extra ball inside of my body-centric cubic. Another possibility is what's called FCC, or face-centric cubic. So instead of having one ball in the middle, I have one ball in the middle of each face. So because I have 6 faces, I can put 6 extra balls in here. Okay, so here's one in the front, there's another one in the back, there's one on the left, there's one on the right, there's one on the top, there's one on the bottom. Okay, this is even more efficient in terms of how to pack as many particles as possible in a certain volume in space.